What if I told you that two of the most fundamental ideas we have, zero and infinity, don't actually exist? Not in the real world anyway. What if our universe, the one we're all in right now, has hard limits, a smallest possible size, and a biggest possible scale? Well, let's dive into this, because this idea really changes how you look at, well, everything.
I mean, we all learn about zero and infinity in school, right? They feel totally real, completely essential to how we understand the world. But here's the big question we're tackling today. If you actually go out looking for them in the physical universe, can you find them? The source material we're digging into argues that the answer is a pretty clear no.
So here's the big shift in thinking we need to make. The argument is that zero isn't actually nothing. It's just a word we use for quantity that's too tiny for us to measure. And infinity? It's not some place you can travel to. It's just our label for a quantity that's too massive for us to get our heads around. They're not numbers. They're placeholders for the absolute edges of our perception.
Okay, so if we're going to explore these wild scales, from the unbelievably tiny to the mind-bogglingly huge, our normal numbers just aren't going to cut it. We need a special kind of map, a new way to talk about these distances, to navigate the full scope of reality.
And that map is something called magnitude notation. Now, it sounds complicated, but I promise it's super simple. You just put a number inside parentheses. So a positive number, like 3, that just means 1 with 3 zeros after it, 1,000. A negative number, like -3, that's a decimal point, 2 zeros, and a 1, 1,000th. Every single number you go up or down is a massive 10x jump. It's the perfect tool for the journey we're about to take.
All right, map in hand. Let's do this. First, we're going on a journey through time. We're going to start at the absolute oldest thing we can measure and zoom all the way down to the shortest possible flicker of existence.
Here we are, the very top. In our new notation, 17.64 seconds is the estimated age of our universe. That's a number with 17 digits. It's our ultimate upper limit. You can't measure a time period any longer than this because, well, time itself didn't exist before this moment. This is it, the beginning.
Now let's just plummet down the scale to something we can all feel. -1.0 seconds, a tenth of a second. The time it takes to blink your eye. This is our "you are here" marker on the map. Feels pretty fast to us, right? But on the scales we're talking about, it's an eternity. Okay, buckle up, because we're about to go way, way smaller.
And just like that, we're in the quantum realm. -22 seconds. That number represents the half-life of a Higgs boson. That's the particle that gives other particles their mass. This is a length of time so short, it's basically impossible to imagine. It's an event that's over and done within a decimal point, 21 zeros, and then a 1 of a single second.
And here we are, the end of the line, -44.73 seconds. This is what's called Planck time. And this isn't just a really short amount of time. It is the shortest possible unit of time that means anything in physics. If you go any shorter, our understanding of cause and effect of time itself just completely breaks apart. This is the fundamental tick of the universe's clock. So you see, there's no zero time. There is only Planck time.
Pretty wild, right? Okay, deep breath. Now we're going to do that exact same journey all over again, but this time through space. We're going from the very edge of everything we can possibly see all the way down to the fundamental pixel of reality itself. Our journey starts at the biggest scale imaginable, 26.9 meters. That's the diameter of the visible universe. Why visible? Because light from anything farther away than that simply hasn't had enough time to reach us since the Big Bang. This is our observable edge, our practical, physical infinity. Now let's come crashing back down to something familiar, our anchor point, 4.0 meters. Roughly the thickness of a single human hair. Seems unbelievably thin to us, but you're about to find out just how gigantic that really is. Let's take another huge leap down the rabbit hole, to -15 meters. This is the world of the atomic nucleus, that super dense little core where almost all the mass of an atom is hiding. And as incredibly, mind-bogglingly small as this is, we're still not at the bottom. We can go smaller.
And thud, we've hit the floor. Again! -35.2 meters. This is the Planck length, and just like Planck time, it's the smallest possible distance that makes any sense. It's the scale where the smooth fabric of space-time breaks down into a kind of grainy quantum foam. It is the absolute fundamental pixel of our universe. There is no zero distance, there's only the Planck length.
Okay, so we've taken these two unbelievable journeys.
one across the entire range of time, and one across the entire range of space, from the absolute biggest we can measure to the absolute smallest. And now we get to the part that is just truly mind-bending. Let's put those two journeys right next to each other.
So get this, the entire measurable range of time, from that tiny quantum tick all the way up to the age of the universe, spans about 62 orders of magnitude. Now what about space? From that fundamental quantum pixel all the way out to the edge of the visible cosmos, it also spans 62 orders of magnitude. They're the same. The total scale of reality is the same for time as it is for space.
Now, you might be thinking, is that just some random cosmic fluke that these two fundamental scales of our universe just happen to match up? Well, the author of our source material has a pretty snappy thought on this. As they say, coincidence? I think not. This doesn't feel like an accident. It feels like a deep clue about the way our reality is put together.
So what does this all mean? What's the big takeaway from this weird cosmic symmetry and this idea that there's no true zero or infinity? It tells us something really profound about the kind of universe we're actually living in. Okay, let's boil it all down. Takeaway number one. Zero and infinity are incredible tools for math, but they aren't physical realities. They're just concepts we use for stuff that's beyond our ability to measure. And number two, our universe has hard boundaries. It's finite. The upper limits, the biggest things, are set by cosmology. You know, the Big Bang and the speed of light. And the lower limits, the smallest things, are set by quantum mechanics, the point where reality itself gets pixelated.
And all of this leaves us with one final, awesome question to ponder. If our reality isn't infinite, if it's contained inside these 62 orders of magnitude, what happens if you go to the edge? If you could actually travel to the Planck length, or exist at that very first tick of time, what's on the other side? What lies beyond the measurable?